Okay, here I have a tank, a reservoir, which I'm going to fill with water. This pump is then going to take the water from the tank, pressurize it, and send it to this little nozzle, which is going to inject the water into the engine. Okay, so that's the plan. Now let's install all of this onto the car. Okay, so here's the setup installed. Here's the tank with the water. There's a line going from the tank to the pump, and then another line continues and goes into the engine bay right here. It enters and then it gets injected right here. There's a nozzle there underneath this cable for the throttle body. It injects water here before the throttle body and the intake manifold. And how much water and when is it being injected, it's controlled by this controller, the electronics right here. And inside the car I have this little display which also tells me what's going on, how much water when, and this little light which glows red when the tank is completely empty. So now let's fill up the tank, fire the car up, and take it for a spin. So we measured 273 horsepower and 373 Newton meters of torque, but this is at 5,500 RPM, and this engine is capable of revving to 7,000 RPM, but we couldn't get to 7,000 RPM because the boost pressure kept popping of couplings and destroying hoses and whatnot, and eventually we ran out of time and had to call it a day. So the engine is capable of making more power if we can get to the red line in the future. In case you're wondering, this engine is a 1.6 liter Toyota 4AFE engine, a economy Toyota engine from the 90s, taken from a Carina E, turbocharged and transplanted into my MR2 Mark I. The previous setup without water injection was 198 horsepower at 6,700 Newton meters of torque, so definitely a big increase right here. Okay, hold up, what just happened? How does injecting water into an engine make more power? Because water is an incompressible, incombustible liquid. It doesn't really belong inside an engine, does it? Well, of course, the water is not what's making the power. What the water is doing is enabling the engine to run a much more aggressive tune, and that's what's making the power. And that works because we are making the engine sweat on the inside. I know it sounds like nonsense, but to understand water injection in engines, you have to understand when do you sweat. You sweat when you are hot. Water forms on the surface of your skin, and as that water evaporates, you cool down. That works because water has a very high heat of vaporization. In more simple terms, as water transitions from a liquid to a vapor, it takes away massive amounts of energy in the form of heat from its surroundings. So water forms, it evaporates, it takes away excess body heat. This is also why you're cold when somebody pours a bucket of water. When you're outside, water evaporates, takes away too much body heat, your body struggles to maintain a normal temperature, and you start shivering. We're doing the same thing inside an engine. We are injecting fine droplets of water, and as they transition from a liquid to a vapor, they take away massive amounts of heat from inside the engine. And that's good because excess heat is the ultimate killer of power and efficiency inside an engine. Most gasoline engines, especially those with a turbo or a supercharger, are limited by knock and or pre-ignition. Knock and pre-ignition are not the same thing. Pre-ignition occurs before the spark plug fires, when the piston is still going up. Pre-ignition usually destroys an engine pretty quickly, and it can easily burn a hole through a piston. Knock, on the other hand, occurs after the spark plug fires, when the piston is going down. Knock can be anything from very mild with minimal damage to very destructive. Excess heat inside the engine is the main prerequisite for both pre-ignition and knock. And inside the engine, we manage the following three things to avoid pre-ignition and knock, and they are intake air temperature, air-fuel ratios, and ignition timing. As the name implies, intake air temperatures refer to the temperature of the air inside the intake manifold. This is the temperature of the air right before it goes into your combustion chamber. The higher the temperature of this air, the greater the chance of knock and pre-ignition. This is why almost all turbocharged vehicles have intercoolers. Before going to the engine, the air gets passed through the intercooler, which has thousands of little fins for a maximized surface area, so that it can pass as much heat from the intake air onto the surrounding ambient air outside the engine. The intercooler cools down the air, leading to greatly reduced intake air temperatures, which helps prevent knock. But for an intercooler to work, we need good flow of outside air over the intercooler. And as you can see in my case, we don't have that. The intercooler is in the back and it's in a horizontal position, so it's definitely not exposed to good airflow, which leads to high intake air temperatures in all but the coldest of weather. Starting with 19 degrees ambient air temperature, here's what my intake air temperature looks like after 22 kilometers of spirited driving on an open road. As you can see, that's 40 degrees Celsius above ambient. But things would get even worse in summer. When I first tuned this car, it was summer and ambient temperatures were around 36 degrees Celsius. And what happened once was that after driving hard, I had to come to a stop due to some roadworks. I had to wait for a few minutes, and during those minutes, I watched my intake air temperatures reach a bit over 80 degrees Celsius. As I took off, my ECU registered a knock spike. Of course, I panicked, as seeing knock on a brand new engine is never good, so I proceeded to immediately remedy the problem. And I did it by modifying my air-fuel ratios. Of course, air-fuel ratio refers to the ratio of air to fuel going inside the combustion chamber. Usually the best power at high RPM and wide open throttle is made when we have an air-fuel ratio of around 12.5 to 1. That's 12.5 units of air to 1 unit of gasoline. To play it safe, I was running 12 to 1 back when I first tuned the car. When I experienced knock, what I did is that I immediately changed all my air-fuel ratios in boost from 12 to 1 to 11 to 1. This is a richer air-fuel ratio. In other words, we have more fuel inside the combustion chamber. This increased quantity of excess fuel cools down the chamber as it vaporizes, just like sweat, as I explained at the beginning of the video. But 11 to 1 is not the ideal air-fuel ratio for power, so my power dropped off and my fuel economy was also negatively impacted. But knock never happened again. But gasoline sucks at taking away heat compared to water. That's because the heat of vaporization of gasoline is around 400 kilojoules per kilogram. So it takes 400 kilojoules of energy to vaporize just 1 kilogram of gasoline. The heat of vaporization of water is 2,260 kilojoules per kilogram. So water is dramatically better at taking away heat from its surroundings. So what I did after I installed my water injection system is that I changed my air-fuel ratios under boost to those for best power, which is 12.5 to 1. And I never had to worry about pre-ignition or knock ever again in any weather, because water is great at taking away heat from its surroundings. Although the primary benefit of water injection is to cool the chamber, it also helps to cool intake air temperatures, because the water is injected here before the throttle body, before the intake manifold, so already it starts vaporizing a bit there and takes away some heat from the intake air. And here you can see my intake air temperature after that same 22 kilometer spirited drive on the same road, same day, same ambient temperature. I reduced intake air temperatures by 5 degrees Celsius. Not much, but it definitely helps. But more importantly, I have to come clean. I wasn't able to achieve my final power figure with water injection alone and just leaning out the air-fuel mixture. This gave me only around 16 horsepower. My final power figure was achieved when I mixed water with alcohol.
Now, alcohol or ethanol is great because, unlike water, it is a compressible and combustible fluid, just like gasoline. But it's better than gasoline. If we put ethanol and gasoline side by side, we can observe the benefits of ethanol. As you can see, gasoline has a higher net energy content, but ethanol has a much richer air-fuel ratio for best power. But this is not the primary benefit of ethanol. The primary benefits are that it has a higher heat of vaporization, so it cools the chamber better than gasoline, and it has a higher octane rating compared to gasoline. The octane number refers to a fuel's resistance to knock. The higher the octane number, the greater the resistance to knock or spontaneous self-ignition of the fuel. So what's the ideal ratio of ethanol to water? Well, the common practice is to mix 50% water and 50% ethanol and inject it into the engine.
Now, something that's very important to understand here is that if you took this glass of water and this glass of ethanol, mixed them together and injected them into your engine, this would not be 50% water and 50% ethanol, even though the volumes are equal. Allow me to demonstrate why. Here's the water. And here's the ethanol. And as you can see, the water weighs a bit more than the ethanol. This is because water is a bit more dense than ethanol. And this is why we do not measure volumes of the things we put into engines, such as air, gasoline, other fuels, and in this case, water and ethanol. And that's because volume and the density changes with temperature. So if we measured volumes like this, then we would not have an accurate measurement of what's actually going into the engine, because the density changes as temperature changes. This is why we measure mass. The stoichiometric air-fuel ratio of gasoline, which is 14.7 to 1, is 14.7 units of mass of air to 1 unit of mass of fuel. So if you want to put an actual 50% water, 50% ethanol mixture into the engine, you need to put and measure a slightly greater volume of ethanol to get an actual 50-50 mixture.
So with ethanol and water in the mix, I not only reduced the heat in the chamber, but I also increased my resistance to knock. And this allowed me to do two things. One, increase my boost pressure, and two, increase my ignition advance. Increasing boost pressure, of course, increases power, but it also introduces additional heat into the system, leading to increased risk of knock. But I can reintroduce heat into the system because I have taken away a lot of heat with water ethanol injection. Increasing ignition advance can also increase power, but it too increases pressure and heat in the chamber and leads to an increased risk of knock. It is here that the increased knock resistance of ethanol helps the most. Here we can see the difference between 10 and 20 degrees of ignition advance. As you can see, by the time that combustion reaches peak pressure, the piston is further down the bore the later we fire the plug. It is obvious how 20 degrees advance can make more power. The piston is much closer to the combustion, which means that more of its energy gets transferred onto the piston. But 20 degrees is also more dangerous because the combustion is building peak pressure in a much smaller space. And that means more heat and more pressure. Even if we manage to cool down the chamber, the heat and pressure spike during this time is so high that knock can occur even with water injection.
So what we ultimately ended up doing on the dyno is to first increase ignition advance by 10% in this area right here, which was our expected peak power area with my starting boost pressure, which was 1 bar or 14.5 psi before I installed water ethanol injection. So we started with this, we got a little increase with our ignition advance, and then we decided to start increasing the boost pressure to see where knock would occur with the water ethanol injection. We first went from 1 bar to 1.3 bar, then we went to 1.5 bar. There were no signs of knock. So then we decided to just go crazy and try 2 bar, which is the maximum boost pressure I can produce with my current wastegate and boost controller combination. And even with 2 bar, there were no signs of knock. We could never get to the red line because the boost pressure was too much. It kept knocking off, popping off couplings and destroying hoses. And we eventually ran out of time trying to fix all that, and we called it a day. But even with that much boost pressure, there was so double my original boost pressure, there was no knock. We even had consistently high intake air temperatures of around 50 degrees Celsius, but still no knock. What I should add is that I could have perhaps achieved an even higher power output by running methanol instead of ethanol. Methanol has an even richer air-fuel ratio for peak power and an even higher heat of vaporization, but methanol is also toxic and so cannot be legally purchased by individuals in most countries in Europe, so I went with ethanol instead, which is very close in performance and isn't toxic. But wait, there's more, because with water ethanol injection, I never have to worry about carbon deposits in my engine ever again, because the water alcohol solution acts almost like a steam cleaner inside the engine, and it keeps the insides permanently carbon deposit free. So with all these benefits, we have to ask ourselves, why don't cars come with water/methanol/ethanol injection from the factory if it's so good? Well, cars don't come with this yet. I think that pretty much every turbocharged car nowadays would benefit from a only water or water ethanol or water methanol injection system, because nowadays we have engines which are 1 to maybe 1.6 liters, and we're making 120 to 300 horsepower from engines which are so small. Of course, making such big power from such a small displacement means that we need a lot of boost pressure. And a lot of boost pressure means that we're making a lot of heat. So if you take such an engine, take a hot summer's day, put it in stop and go traffic, things get very hot very quickly. And being a factory engine, it has nothing other than gasoline to work with. So when it senses that tiny little bit of knock, it's going to inject a lot of extra fuel and keep injecting it to stop and or prevent knock in these conditions. And if you owned or own such an engine, I'm sure that you have noticed that in such conditions, a lot of heat, stop and go traffic, these engines are fully incapable of getting anywhere near their advertised fuel economy. So with water injection, we could cool things down and restore power and restore fuel economy to such engines. Now, this isn't happening yet, but it has been experimented with in the past. There was a very famous instance. It's the Oldsmobile Jetfire in the States back in the 60s. It had water methanol injection from the factory. Americans being Americans, they called it rocket fuel. The problem was that the rocket fuel was very expensive, so owners didn't really keep the tank topped up, so the car wasn't really a success. But now, when we have ever increasing, ever more stringent emissions, fuel economy standards, water injection is again being experimented with. And the latest attempt is from Bosch and BMW, which have co-developed a system that, which is very important, does not need topping up. You don't have to worry about it. It does its thing by scavenging water from the operation of the air conditioning system. So no topping up. Whether it happens in the future, whether it becomes mainstream, we will see, but the benefits are undeniable. And as we go even further into ever smaller, ever more powerful engines, I think water injection systems might be more prevalent in the industry. So if I had to sum it up in one sentence, I would have to say many problems, but one pretty effective solution. So that's pretty much it. As always, Thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.